Now in part 3, I would like to describe the locally constrained curvature flows in hyperbolic space. The flow was introduced by Brando, Guan, and Li recently. We first describe the definition of this flow. In this part, we view the hyperbolic space as a vector product, which means that we identify the hyperbolic space as R plus product with the unit sphere equipped with the metric dr square plus sinh square r times the round metric. And a hypersurface M in the hyperbolic space is called star-shaped if its support function U is positive on the hypersurface. Here, the support function is defined as the inner product with inner product of sinh r with the unit normal vector nu. Equivalently, this means that the hypersurface can be written as a radial graph. Then for k-convex, as we mentioned in part 1, this means that the S-mean curvature I is positive for all I up to k. Then for k-convex and star-shaped initial hypersurface, we consider the following flow. The curvature term in the speed of the flow is the quotient ek minus 1 over ek. There are some other terms in the speed, which is the cosine r and the support function. The speed of the flow looks a little strange, but it is well motivated and is based on the Minkowski formula. For closed hypersurface, we have this integration formula. The left-hand side is a weighted integral of the case-mean curvature ek, and the right-hand side is the integration of the support function and product with ek plus 1. And here ek is the case-mean curvature. So from this Minkowski formula, we see that the flow by Brando Guan Li has a very nice property, which preserves the case core mass integral Wk and decreases the k plus 1's core mass integral Wk plus 1. This can be proved by a direct calculation. For example, we see that the time derivative of Wk is given by the integration of the speed of the flow times ek. And this integration is equivalent to the Minkowski formula. So this is 0, and the Wk is preserved. And similarly, we see that the time derivative of Wk plus 1 is the integration of the speed times ek plus 1. And then here we apply a Newton-Maclaurin inequality, and then see that the ek minus 1 times ek plus 1 over ek is smaller than ek. Then we again see that this integration is equivalent to the Minkowski formula. So this is 0. Now we have that the Wk plus 1 is monotone decreasing and Wk is preserving. The next step would be to show the convergence. So the goal is to show that the flow converges to a geodesic sphere for general k-convex and star-shaped hypersurface. If this can be proved, then we can compare the initial values of Wk and Wk plus 1 and with their limit value, which can be a constant. And this gives the Alexandra-Fincher inequality for k-convex and star-shaped hypersurface. However, so far only some special cases have been considered. In Brando Guan Li's preprint, they considered the following two cases. The first case is for k is n and the initial hypersurface is convex. And the second case is for general star-shaped and k-convex hypersurface, but they need to assume a gradient bound, which is a bound on the gradient of the radial function of the initial hypersurface. Then in either of the above two cases, we can prove that the solution of the flow exists for time and converges exponentially to a geodesic sphere. The condition 2 is artificial and is only used to prove the C1 estimate of the flow. So it's a question that whether we can remove this condition. There are some remarks about this flow. The flow is a locally constrained curvature flow because the speed of the flow is a pointwise defined function without global terms. This is in contrast with the globally constrained curvature flows that we mentioned in part 1 and part 2 of my talk. There is a global term phi t in the speed of the flow, and choosing to preserve some core mass integral. And for the convergence result of Brendel-Guanidis flow, a key step in the proof is the C1 estimate. Because the speed of the flow is a pointwise defined function, we can apply the comparison principle. Note that the geodesic sphere is stationary along the flow, so we can apply the geodesic sphere as a barrier to conclude the C0 estimate. Then once the C1 estimate is established, the C2 estimate is equivalent to the curvature estimate. Then this can be deduced from the evolution equation of the second fundamental form. Now I describe our result on Brendel-Guanidis flow. This is a joint work with Haizhong Li and Yin Xianghu. We didn't solve the question asked by Brendel-Guanidis. Instead, we observed that the h-convexity is preserved along the flow. Then we can show that the flow converges to a geodesic sphere starting from the initially h-convex hypersurface. Then secondly, we find more applications. We can apply the convergence result to prove some new optimal geometric inequalities. Now the following is the k-lemma of our result. We showed that if the initial hypersurface is h-convex, then the solution mt remains to be h-convex for later time t. And the method is to apply the generalized tensor maximum principle by Andrews to the evolution equation of a tensor Sij, which is defined as the difference of hij and gij. And note that the h-convexity is equivalent to that the principal curvature greater than 1, which is also equivalent to that the tensor Sij is positive definite. If we denote the curvature terms ek over ek minus 1 by f, then we can calculate that the tensor Sij satisfies this evolution equation. In this evolution equation, we see that there is a second order term and the first order term, and there are some remaining terms which are complicated. To apply the tensor maximum principle, we need some condition on these remaining terms. Whenever there is a point x0, t0, and the tensor Sij has a null vector nu, we need that the blue term in the bracket satisfies that the beta nu plus the red terms non-negative. And this is just the condition for Andrews tensor maximum principle. Then we can conclude that the tensor Sij positive can be preserved for positive time. Now, once we have the h-convexity, we can combine this with the C0 estimate to deduce the C1 estimate, and then to deduce the C2 estimate and the CK alpha estimate by a standard argument. And finally, we obtain the smooth convergence to a geodesic sphere. Now we state our main theory. If the initial hypersurface is h-convex, then the solution remains to be h-convex, and the solution converges to a geodesic sphere. Then recall that the Brendel-Guanidis flow has a very nice monotonicity property. So combine the monotonicity with the convergence result, we obtain a new proof of Wang and Xia Alexander Fincher inequality for h-convex hypersurface. Moreover, we can find more applications. We can apply the convergence result to prove new optimal geometric inequalities. And I will state the new geometric inequalities in the following. This is the first inequality. For h-convex bounded smooth domain omega in the hyperbolic space, whose boundary is denoted by m. Then we can compare the integration of the Gauss-bounded curvature LKG of the boundary with the core mass integral Wm. Here the LKG is the k-Gauss-bounded curvature, which is defined in terms of the Riemann curvature tensor of the induced metric on the hypersurface. Recall that a hypersurface M in the hyperbolic space, we can apply the Gauss equation to relate the curvature tensor to the second fundamental form. And then we see that the Gauss-bounded curvature LKG can be expressed in terms of linear combination of the K-mean curvature. So here to prove this inequality, we apply the flow by Brendel-Guanidis, and this flow preserves the right-hand side Wm, and then we need to calculate the evolution equation of the left-hand side. So based on this equation, we can just need to calculate the evolution equation of the integration of the K-mean curvature, and eventually we see that along this flow, the m's core mass integral Wm is preserved, and the integration of LKG is now increasing, and for the index m smaller than 2k plus 1. Then we can combine this monotonicity and the convergence result for h-convex hypersurface and obtain that the integration of LKG at the initial hypersurface can be greater than its limit value. And this gives us the desired inequality. We recall that for the index m equal to 1 in the above inequality, this case was proved by Yuxingge, Guofang Wang, and Jie Wu in 2014 for h-convex hypersurface, and later by Hu and Li for hypersurfaces with non-negative sectional curvature. Here we can prove the inequality for all m bigger than 1 and smaller than 2k plus 1. So we obtain some new inequalities. Now this is the second geometric inequality, and for a smooth bounded h-convex domain whose boundary M is a smooth hypersurface, and for K, for general K between 1 and n and m smaller than k, we can compare the integration of the cosine GR times Ek with Wm. In particular, for M is 1, Wm is the boundary area, so we can express the inequality 5 as the following. The right-hand side is a function on the area of the hypersurface. We can write it down explicitly. For k is 1, this inequality was proved by Dilemma and Nigeria in 2014 for mean convex and star-shaped hypersurface. And later for odd k. For odd k, Wang Wu proved this inequality 6 for h-convex hypersurfaces. And now here we proved this inequality 6 for all k. And moreover, we can prove the inequality 5 for all m smaller than k. So we obtain many more geometric inequalities. This inequality compare the weighted integration of the curvature Ek. This types of inequalities could be useful to the Pearson type inequality for Gauss-Bonnet chain mass for asymptotically hyperbolic manifold. Now, finally, I would like to describe some further questions and remarks. Firstly, the Brendel-Guanidis flow for k-convex and star-shaped hypersurface is still an open question. Can we prove the long-time existence and convergence? Secondly, we can ask similar questions for hypersurfaces in the unit sphere. There are some partial results in their preprint. And we can also study the locally constrained curvature flow in other ambient spaces and in the free boundary setting. The following are some recent work, for example, by Xiaoyue, Wang, and Xia in the free boundary setting, and by Guan Li, and Butao Wang, and Xiaoyue, and by Lambert in other ambient space. Now, this is the end of my talk. Thank you very much for your attention.